Ladies and gentlemen, recording has started. So, yesterday we began discussing this presentation called Location of Electrons in the Quantum Mechanical Model, right? And we discussed yesterday that that title, if you don't know what you're talking about, can be misleading, right? Why is that title misleading? Andy, go ahead.
Because you can't find the exact location.
We'll never know the exact location of electrons, right? But we'll only know what, Andy?
How fast they're going, or where they would be.
Okay, and that then comes together as far as our model of the atom goes. What will we know about electrons?
Where they're most likely to be.
Where they're most likely to be, right? Areas of high probability. And what do we call those areas of high probability? What do we call these areas of high probability? Lorna? Orbitals, right? Different than Bohr's orbits, right? Or shells. What did Bohr say about electrons in an atom, right? Eris?
They're in quantized shells.
Quantized shells, right? Meaning that what, Eris?
They can only have specific energy.
Good, and that means that they can only be located at
Those positions.
specific distances from the nucleus, okay? We find out that that's not really the case, right? Electrons can exist everywhere, but there are areas of higher probability, right? And we refer to those as orbitals, okay? They're not orbits, they're orbitals, okay? Good there. All right. So, we started talking about that eventually where we want to end up is this idea of developing a set of quantum numbers for the orbitals that exist around the nucleus, right? And that it's an address, a most probable location for electrons to exist. It's not the exact location, it's a probable location, okay? So we start off with our principal quantum number. And yesterday we looked at the population density map, right? We looked at Ohio specifically and then the Cleveland area and stuff like that. What did we say the principal quantum number sort of corresponded to on the map, Andy?
The state.
Maybe state, maybe a little bit closer to that, maybe more like a city, right? Where if you look at the quote-unquote picture of an atom, right? Okay, it's not a picture, this is just a model, right, to help us understand things, okay? That we got this area right here that's kind of dark, and then this area, there's like a greenish area where not a lot of electrons exist, and then there's a darker area where we find more density, then there's another green area where there isn't so much, and then there's a bigger area where there's a lot of darker stuff, right? So we see these areas of high probability sort of on, off, okay? But, and this is kind of the point of the map activity that we looked at the beginning of class yesterday, right? If we start looking closer at these areas, we start seeing that, yes, this looks all to be very densely populated, and this looks all to be very densely populated, but if we start looking closer, we find that there are some areas within that band that maybe aren't so populated and other areas that are more populated. And we refer to those as sublevels, right? All right, and this is kind of where we left off yesterday, right? So, what we find out is, and let's redraw our picture, okay? Because I had an idea that I wanted to do it differently from yesterday. Stand by. Okay, so we start off, nucleus, right? And then we said that around that nucleus, there is a pretty heavily populated or a high probability area of finding electrons. And I think we call that blue. I think I made it like this, but it doesn't want to do that. Okay, so we got that there. Okay? And we discussed the idea, right? We refer to that as the first principal energy level. it's the area where we first are most likely to find electrons. Is it heavily populated? Is there a high probability of finding electrons there?
Yes.
Yes. Why, Eris?
Because they're close to the nucleus.
Real close to the nucleus, right? And what is the nucleus doing to electrons?
It's attracting them.
Because of the whole positive negative thing, right? Okay? But we also discussed the idea that is there a lot of electrons in that area?
No,
No. Why not?
because they repel each other.
Okay? So we have this balance, right, of the attraction to the nucleus and the repulsion of the other electrons, right? So we got this area, okay? But then there's like a space, okay? But now we have a second area. Remember, this is a two-dimensional drawing of a three-dimensional a two-dimensional representation of something that's three-dimensional. Okay? This, all right, go here. Color? Red. I think we made it red yesterday. So we got this area here. This being our second principal energy level. Okay? Then, on top of that, or outside of that, right, we have our third principal energy level. And then, outside of that, we have our fourth principal energy level. Okay, so we gotta look like this, right? And I kind of made mention to you guys yesterday. Think of it kind of like those like Russian stacking dolls, right? Where one fits into the next, fits into the next, fits into the next. Okay? All right, but let's take away fourth principal energy level and third principal energy level first, and let's focus on the second principal energy level. This is like the second city, right? It's a big area where we have a high probability of finding electrons. But within this area, we find that there are certain spots that are more likely to find electrons and other spots where it's less likely to find electrons, right? So we kind of remove that. What we find is that there is a spherical area. I'm going to do something different. A spherical area that's kind of close to the nucleus, that has a very high probability of us finding electrons. And we refer to this as a sublevel. And specifically, we refer to this as the S sublevel. Okay? But we will find that within that red sphere, there are other areas where electrons start hanging out. Namely, this kind of area here, and this kind of area here, and this kind of area here, and this kind of area here. Okay? These two areas, something I can't do here. These two areas are sort of related to each other. Okay? They kind of, these, oh, I'm grouped them, are you kidding me right now? Okay, there, okay. These two areas are related to one another. Okay? And they end up forming what we kind of refer to as a figure eight-ish sort of shape. Okay? And then these two areas, this one here and this one here, those are related to each other as well. Okay? And we refer to those together as the P sublevel. Now, keep in mind, all of this goes together. And this all goes outside of that first area. Does that make sense? Okay so far? Then, if we add our next principal energy level onto it, right? When we look at the third principal energy level, it starts off with a spherical area, okay? And that's the S sublevel within that principal energy level. Okay? We do this. Hold on. Make this a little bigger. And that in this third energy level, there are also these areas here. Okay? And we still refer to those as the P sublevel. Okay? But now it's the P sublevel in the third energy level. Okay? But once we get here, now we start seeing that there's actually a third sort of area that shows up. And it kind of looks like this. What are we seeing about how these areas are spaced out? Andy, go ahead.
They're filling up in the spaces that don't have any electrons.
Filling up the spaces that don't have any electrons, right? Trying, like we said, to find that balance between being attracted to the nucleus, but then repelling other electrons, okay? But keep in mind, all of this is together, and all of this goes on top of that. Does that make sense? Okay? And then the yellow one even has more craziness going on, so I won't draw it for you. But let's draw the important parts. Okay? Move this down a little bit. Okay. This principal energy level has an S, and it has P, and it has D. Sorry, we'll go P here. Okay, that's P. Okay, and then these areas here we call the D sublevel. I should have wrote that up there, but I didn't. Okay, but keep in mind, right? This all goes together as well, and that together goes on top of that. Okay? Are we seeing this picture kind of, sort of, maybe? Okay? It's kind of confusing. I know it is. All right? But let's get back to why, now that we know that these areas exist, how do we distinguish them? Okay? All right. I think towards the end of class yesterday, I showed you this chart. Is that correct? Is this where we ended up? Okay? All right. So, what we find out is that these areas of high probability start taking certain shapes. And Andy, we kind of said before, that's due to the fact that those electrons are trying to find that mix, right, of where they fit, attractive to the nucleus versus repelling all the other electrons. Okay? So we find out that every principal energy level, every different colored sphere on this picture has an S sublevel. It's the first one, and it looks like a spherical shape, right? The first thing I drew on all of these different levels, oh, apparently that wasn't connected. I wanted it to be connected. Oh, I gotta go back and fix this. The first thing I drew on all of those levels was that sphere, okay? We refer to that as our S. Oh, I unconnected it again. No. The first thing that shows up is that spherical section, okay? Whether it's the red level or the blue level, it's just a sphere to begin with. The red level, the green level, the yellow level, okay? Then, once we got out far enough, we started seeing these different areas, these P sublevels, okay? And they have this kind of figure eight shape to them. Now granted, the other stuff is in the middle, but it's got that shape to it. And then P levels show up in each spot, or each principal energy level, past the first, or the second one, okay? And then D starts showing up. It has these crazy shapes here, okay? And that's where we go, all right? So, how do we distinguish these sublevels? We use the angular momentum quantum number to distinguish all of these sublevels. Okay? First, we use the lowercase letter L. The lowercase letter L. All right? I think on your outlines that I had to use it, I tried to use like a little scripty one so you can tell the difference between an L and a 1. Okay? So, each of those different sublevels has a L value that tells you its shape. Okay? And as we've gone through, those have showed up a little bit, but now we can see them total. That if it's an S sublevel, we give it the value L equals 0, regardless of whether it's in the first level, or the second level, or the third level, or the fourth level. There's an S orbital in every level. So there's a 1s, and a 2s, and a 3s, and a 4s. P orbitals, those comes that kind of look like figure 8 sort of shaped, get the L value of 1. P orbitals don't start until the second level. So there are 2 p orbitals, and 3 p orbitals, and 4 p orbitals, but there is not a 1p. Okay? And then d orbitals that kind of have sort of a crisscross shape, like an X sort of shape, they don't show up until the third level. So there are 3 d orbitals, and 4 d orbitals, and 5 d orbitals, but there is not a 1d or a 2d. Okay? Good there. If we go back to this chart, right, you can see that there's only one s orbital in every level. And levels that have p orbitals, there are 3 p orbitals. One of them goes side to side, one of them goes up and down, one of them goes front to back. So x-axis, y-axis, z-axis. All right? Does that make sense? Kind of like if you think of this as a street in a neighborhood, right? All three of these houses are on the same street, but they're different houses, right? They have something in common because they're on the same street, but they're different houses. And that's kind of what we look at here, right? So the next thing we have to do is we have to distinguish whether we're talking about this house, or this house, or this house, right? And so that's where we get into the magnetic quantum number, which, depending on what book you read, is symbolized a couple of different ways. Sometimes you will see it symbolized as just an M, and sometimes you will see it as an M with a little subscript L, okay? From this point forward, I'm probably just going to call it M, because that's a lot easier for me to write quickly than the M with the L subscript. Okay? So what does this tell us? It indicates which orbital the electron is in within these different sub-levels. Okay? Did I skip one? We'll come back to it. That one's more important for the next one anyway. So like we said, there are 3 p orbitals. But which p orbital are we in? Are we on the one that runs side to side on the x-axis? Or are we on the one that runs up and down, which is the y-axis? Or are we on the one that runs front to back? That's the z-axis. Okay? We have to distinguish that. Now, how many orbitals there are is determined in some way by the L value, right, or the angular momentum quantum number that we wrote down previously. Okay? Possible values for the magnetic quantum number run from negative L to positive L. Right? So that means for a p orbital, its L value is equal to 1. If we run from negative L to positive L, that means these magnetic quantum numbers will start at negative 1, and then you got to go through 0, and then you got to go through positive 1. If you look at your chart on the previous page, how many possible p orbitals are there? there's 3. And these are the 3 values that we use to distinguish this one from that one from that one. Okay? For the d orbitals, its L value is equal to 2. If we go from negative d to positive, or sorry, negative L to positive L, that goes negative 2, negative 1, 0, 1, and 2. If you flip over to your chart on the previous page, how many d orbitals are there? There are 5. And so we have to have a way to distinguish this one from that one from that one. Or a way to distinguish this house from that house to that house. They're all on the same street. Which house are we living in? Okay? Good there. All right. The last quantum number. We talked about the idea that orbitals are areas of high probability of finding electrons. But are we going to find too many electrons in the same spot?
No,
No, right? Why not, Mark?
because if they're since they're repelling each other, they're not going to be very close to each other.
Right.
And
That this may be a good spot for one electron, right? But as soon as another electron moves in, okay, it's still kind of all right, but if a third electron moves in, now, it's blown, right? It's not a good spot anymore, okay? So these areas of high probability can only contain so many electrons. And that brings us then, you guys wrote that down already, right? That's on your outline. All right. Those areas of high probability have a limit as far as how many things they can hold. And then we refer to that as the spin quantum number, okay? We symbolize that by the letter, depending on the book you read, right? M with the lowercase s, or from now on, I'll probably just go S. I should really change that, but I didn't. Sorry. Each orbital can only hold 2 electrons. We refer to this idea as the Pauli exclusion principle. Okay? It didn't take probably a real genius to figure out why can an orbital only hold 2 electrons. We kind of just discussed it. Eris, go ahead.
Because if 2 electrons move in, they already repel each other, and if the other one moves in, it'll repel more.
If a third one moves in, it's messed up, right? It's not good anymore, okay? So think of it like, okay, we said the last one was kind of like the houses on the street, right? Think of this as kind of like maybe a room in that house, right? So if you're in your family, like I have 2 kids, right? And my house has 3 bedrooms, one for me and my wife, one for my son, and one for my daughter, right? If we have another kid, messed up, right? Not necessarily, but just use it as an example, right? That house is good for us. We all got our own space. Everything's good, right? But if we have another kid, boom, now we got to make some arrangements, right? And I'm sure either my son or my daughter would be like, this is messed up. It doesn't work for me anymore, okay? So think of it that way, right? That each orbital can only hold 2 electrons. But we have to distinguish that space that the one electron holds from the other space that the other electron holds. We say that they have different spin, quotation marks. Does that mean that the electrons actually spin one way versus the other way? No. Okay, it's not what it means. It's just a way to distinguish one from the other. Okay? And so, spin quantum number only has to have 2 values to distinguish between this electron and that electron. Because once you go past that, now we're talking about a different house, right? So the possible values for the spin quantum number are only +1/2 and -1/2. That's it. There's only 2. Okay. All right. Good with that so far. I know it's kind of confusing, but let's start talking about it a little bit. Okay. All right. Here's what I'm going to do. You guys don't have this picture, but I do. All right? So, I'm going to do some stuff up here on the board. Okay? I just want you to watch, and this is what I will do. I will post the notes that I'm going to write here up on the board right now after class. okay? So if you want a copy of the stuff I'm going to write up on the board right now, it will be there for you this weekend or later today or whatever, okay? Good there? Okay. So here's our full atom with a bunch of orbitals, right? Areas where electrons probably exist around the nucleus, okay? Good there. All right, here's what I'm going to do. I'm going to take this page and I'm going to make a copy of it, okay? So that we can mess around with it, talk about little individual parts, all right? So let's take this level off, let's take this level off, all right? And let's focus on the red level, okay? Okay, so first quantum number that we came across yesterday, what did we call it? N, right? And that's the N is represent what's quantum number, Mark? What do we call it? Do you remember its name?
No idea.
Okay, so N is what we refer to as the principal quantum number. Okay? All right. And that tells us which principal energy level we're discussing. So let's say we are talking about an electron that is right there in that spot that I just drew. Okay? So, which energy level is it in? We said, oh, sorry, let's go to this. We said N values get numbered how? Go back and look at your notes, right? How do N values get numbered? Eris?
Are there principal energy level?
Okay, so and that means that they go up how? 1, 2, 3, 4, right? Okay. So what would N be for this electron that I just drew right here?
2.
2, right? N is going to be 2 for this electron because it's in the second principal energy level, right? It's in the red value, which is the second shell around the nucleus, okay? Quote unquote shell, not Bohr's shells, but okay, good there. All right. What kind of an orbital is it in? What shape is it in, Andy?
It's in the p orbital.
It's in a p orbital, right? And we said that the next quantum number, right, we refer to as L, right? And that's the angular momentum quantum number, right? Okay. Angular momentum quantum number tells us the shape of the orbital that that electron is in. Right? Because, Andy, you told us it's in a p orbital, right? What value does L have for p orbitals?
1.
1. Okay? So we're starting to piece together an address here. Okay? Now, the next one's a little tricky. Okay? The next one is a little tricky. We said the next value is M, right? And that's what we call the magnetic quantum number, right? Magnetic quantum number, okay? What did we say that the magnetic quantum number tells you? I know it's a little, Andy, go ahead.
Which orbital the electron is.
Okay, and we said that magnetic quantum numbers run from negative L to positive L, okay? Now, in this case, right, we called this one the x-axis, right? And if you look on your notes, I kind of decided which one was going to be the x-axis. So what value did we give to M for the x-axis one, Eris?
-1.
Okay, so -1. All right? Good there. Okay. All right. The last quantum number, actually I'm going to skip that for a second and do something different, okay? Let's say there's another electron. One right there. Right? What's its N value? 2. What's its L value?
1.
1. What's its M value? -1. It's still on the x-axis, right? Okay? But this place is different than this place, right? So we got to distinguish between this place and that place. And that's where the last quantum number comes in, right? The spin quantum number. Right? So we got to distinguish between that place and the other place, right? So we said that spin quantum number can only have 2 possible values, right? What are the 2 possible values?
1 and 2.
No.
1/2 and -1/2?
1/2 and -1/2. Jeremy, does it matter which one we call 1/2 and which one we call -1/2? Good guess, okay? Because it doesn't really matter which side is which, right? They just have to be different, okay? So we can call this one +1/2, and we can call this one -1/2. Could you have flipped them around? Sure. But the important thing being, right, all of these numbers, there's a different set of numbers for this one versus that one. Okay? Good there. All right. Want to try another one? Let's do this one. All right. So, because this is the first one you're going to do on your own, all right? I'll give you kind of an easy one to begin with, all right? I'm taking off yellow, taking off green, okay? And I will give you guys an electron that is right there, okay? See if you, actually I'll give you 2 electrons. This one and that one, okay? Talk to the person next to you and see if you guys can figure out what the quantum numbers would be for those 2 electrons, okay? I know you don't have the picture, it's up here, let's see what you can do. Talk, go.
I don't know.
Because it's the same thing as the last, axis last time, so I'm about the same angle, so it has to be the exact. Okay, so basically, so it's 0. X doesn't have to be.
Yeah, 1/2.
Now it makes sense. 21. Yeah, that's y axis is going this way. So this one applies to it down here, right? Okay. And then for B, don't worry about the I just had to get rid of that, but I apparently forgot to worry about the outline.
All right, so there's our set of quantum numbers for these 2 electrons, okay? First, questions. Start with that. Eris, go ahead.
Why is M 0 instead of 1?
Okay. M values, the possible values for M are related to the possible values for L, okay? So this is, first off, Eris, what kind of sublevel are we talking about here? S, because it's a spherical shape, okay? But if you look back at your chart in your notes, right, just for people who are watching the recording, because I know so many people are going to watch this recording. So if you look, right, how many s orbitals are there in each level?
1.
Just 1, okay? So if we go here, right, we said that the possible values for L run from, or sorry, the possible values for M run from -L to +L, okay? What's the L value for an s orbital? 0. So if you go from -0 to +0, right, how many possibilities is that?
1.
Just 1, okay? Because there is only one s orbital in each level. Okay? So when we're talking quantum numbers, if L's 0, M is automatically going to be 0. Automatically, because there's only one possibility.
So when the electron's on the S, M can only be equal to 0.
And then because L is equal to 0. Does that make sense?
Yep.
Okay. And then to distinguish the two of these, right, one's got to be positive 1/2, one's got to be negative 1/2. Okay? Does it matter which one we call positive 1/2 and which one we call negative 1/2? No. If you don't like this choice right here, okay, blame Jordan, because I asked her which one I wanted to call positive, which one to call negative, so she chose this one. Okay. Good there. All right. Ready to increase degree of difficulty a little bit?
Yes.
Yeah. Andy, that's what I'm talking about. Good attitude, Andy. Yeah. All right. All right. So let's get you a new atom here. Okay. Okay. And all right, let's strip away yellow. Okay. And let's talk about. We're going to focus on green here. Okay. Let's talk about this electron here and this electron here. Okay? Discuss. Go.
Can you put them in a different color?
So, right here, okay? And then right here. Actually, let me see what other color options I have, Andy. Here, I'll use orange. That electron there, and that electron there. Okay. Those are p orbitals that those are in. Okay, those are p orbitals. They're in two separate p orbitals.
So we have to have two separate sets of quantum numbers.
Because each electron is going to have its own set of quantum numbers.
Okay.
Right? Yeah. You need two different ones. Okay. Which axis is that? Y axis. What did I call the y axis? What did I call the y axis? Next page. What did I call the y axis? For M is 0 for that one.
Are they still on 1/2 and 1/2?
They could be. Doesn't matter. What did I give you for the y-axis in your notes? M equals what? And this is a y-axis value, right? Okay.
Well, then what's Z value? Doesn't Y go?
Yeah, I always think of y as going straight up and down, like in math class, you know, x-axis, y-axis.
Okay.
All right. Oh, so, like I said, I will post these online so you can take a look at them. For the weekend, if you would, the sheet that I gave you today, okay? See if you can try it out, see how it works, okay? I have answers posted online. We'll talk more about it when you get back, okay? Have a good weekend, everybody.